to your
Hold
Zoom
on
screen, I will
tight.
tell you.
I'm holding.
Hold on tight. Oh, it says live. It says we're live. It says we're live.
I'm holding on tight.
Hold on. Yes, hold
Okay.
on.
Are we live?
You're live. You're live. I'm just going to make sure I've got the right screen here.
Heartbeat. Kaboom, 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 kaboom.
I've discovered if I mute myself and then consciously unmute myself, then I don't interrupt what you're doing. So is it, oh my goodness, yes, we're late for a very important date. It's 20:01 in beautiful London, England, and we have James Tanton. I'm so delighted. I'm hoping he'll come on as a regular because I talk about making maths fun. James talks about joyous maths. Is it joyous? What else do you call it?
Joyous, joyful, and enjoyable. How's that? Anything with J-O-Y in it. That's it.
Joy in it. Brilliant. I love it. And James has created a global organization. He and I had a similar vision, but James has much greater reach than me. And I knew that in order to spread the joy of maths around the world, it needed a whole bunch of people to come together and do it. And James has created that in the Global Math Project. It's got ambassadors all over the world, and I'm one. And James has created some fantastic resources. And good day math. There'll be links in the comments below when we finish, and there's links in the event as well. And James, without further ado, I'm going to mute myself so I don't accidentally interrupt you.
Excellent. I will share my screen when the time is right, but for now, I'm going to hold up my piece of paper. My title page is that. I don't know if it's backwards or forwards for you, but it's exploding dots is the topic of today. In fact, I'll give a gentle introduction to this. So really, I have to tell you, I went through my schooling back in Australia some, long time ago, 30, 40 years ago. And I went through a miserable experience in my schooling in, primary school and high school. It was just joyless mathematics. It was just basically worksheets, just memorize and do, and never ask a question. In fact, I was really shut down when I tried to ask questions. So I learned not to. I did not enjoy it. So it wasn't until university level that I actually fell in love with mathematics, for sure, because it's all about the thinking, the doing, and the why questions, and the what if questions, just the exploring and the playing. Answers and computation are just secondary. They actually don't really matter, because you'd always get answers and computations done quickly if you had to. It's really the thinking behind it all that was it. So then I actually devoted my career to, okay, let's make mathematics joyful in experience for everyone at whatever level of education they're at. So I moved to the US back in 1988. I've been here for the last 32 years. And part of my career has taken me all across the education spectrum. And at one point, I decided I was going to really focus on high school mathematics. It's not what I'm going to talk about right today, but high school mathematics, because I felt like, yes, you can do some good playful mathematics in the earlier grades, and people do, which is great. But then high school sort of gets to this mentality like lockdown for exams, where we get those kids into uni, and our job is to get them into uni. And I had to teach something called dividing polynomials to 15-year-olds. Like, who in their right mind wants to divide a polynomial? Did I ever divide a polynomial as a research mathematician? Not that I can remember. But the thing is, if it's done as the human story about why humans cared about it in the first place, then let it be a joyous human story. And that thinking is what counts, not the actual act of dividing polynomials. So that led me on this journey that Carolyn talked about of the Global Math Project, because it's really the story about the beginning of mathematics. And that story I'm going to present to you today, at that very beginning journey, is as exploding dots. But to do mathematics, you actually have to have pencil and markers and so forth. So I'm going to share my screen, if I can make this work. Share screen, but let me. No, the host has disabled me from sharing my screen. So I need the host to actually give me permission to share my screen.
Hold on. How do I do that?
Manage participants, maybe?
I actually did make co-host. There you go.
Let's try this again then. Let's see what happens. Share the screen. There we go. Now you can probably see, you can probably see the email for this, but what I want you to really see is my screen here. Hopefully you're seeing that piece of paper I was holding up to the camera now on your own Z's. All right. So this is a magical story. This is a human story of the beginning of mathematics. It's one of humankind's greatest achievement is learning how to think about and write numbers. So this is a story that actually starts by assuming we know nothing. We'll start with kindergarten math, not less. And the next 24 minutes we have left together, let me bring you up to some sophisticated mathematics, verging on getting onto the high school maths. And if this goes so well, we can do a second part and actually see how high school maths is the big secret. It's really just a repeat of grade 4 and grade 5, and no one tells you, at least when it comes to polynomial algebra. So let's do all the maths, really doing high school maths in disguise, but assuming we know nothing, and it's all going to begin with a story that's not true. Here's my story that's not true. When I was a child, I invented a machine, and all my machine was a row of boxes going as far to the left as I pleased. So it could be 4 boxes like I've drawn here, or 7 boxes, or 92 boxes, or 1,092 boxes, as many as I want to the left. And being a somewhat strange child, I gave this machine a strange name. I called it a 2-1 machine, written in a funny backwards way, because, you know, I'm a young child and you know different. That's fine. Okay, so then what you do is a machine. You always put in dots. Dots will always go into the rightmost box. But I'm going to start with 1 dot. In fact, here's an actual dot. Here it comes, zoom, into the rightmost box. And nothing very exciting happens when there's 1 dot. It just stays as 1 dot. However, put a second dot into the machine, always the rightmost box. Here it comes, zoom. Well, then something exciting happens, because whenever there are 2 dots in a box, they explode and disappear, kaboom, and are replaced by 1 dot, 1 place to the left. 2 dots became 1 dot, hence my name, 2-1 machine. 2 dots become 1 dot. That's it, that's my machine. And I look at this picture right now, I've got no dots, no dots, no dots, no dots, no dots, 1 dot, 0 dots. I'm going to say the code for 2 in my weird machine is now 1 dot, 0 dots, 1, 0. I won't bother about beginning zeros. Here comes the 3rd dot, always the rightmost position. Here it comes, zoom. Nothing happens, it's going to stay as nothing, 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 1, 1. Now I have a feeling putting in a 4th dot is going to be particularly exciting. Here it comes, always the rightmost box, zoom. Whoops, 2 dots in a box, kaboom, they explode away and replaced by 1 dot, 1 place to the left. 2 dots in a box, kaboom again, they explode away. 1 dot, 1 place to the left. So now 4 has become nothing, nothing, 1 dot, 0 dot, 0 dots. Well, this is great fun. I'm going to keep doing it because I'm just having fun. I'm a young child who's doing this for the pure fun of it. Why am I doing it? I don't know, because it's fun. Here comes the 5th dot, rightmost box, zoom. 5 is 1, 0, 1. Here comes the 6th dot. In fact, pause. Can you see in your mind's eye what the code for the number 6 is going to be in the strange 2-1 machine? Can you see it? Here it comes, rightmost box, zoom. Kaboom, dot. And voila, 6 is 1, 1, 0. And hours of fun, 13. Ooh, 13. I skipped some numbers. How annoying of me. 13. Well, I guess the question is, I don't really know what this machine is doing. So the correct answer to this one is right now, hard. That just seems hard. So I'm going to write hard. Anyhow, I'm just a young kid in this untrue story, just having fun working out codes for different numbers in this weird 2-1 machine. But then one day, I had a flash of insight because I realized instead of a 2-1 machine, I could be crazy and instead do a 3-1 machine. So how would that one work, a 3-1 machine? Well, I guess now it's going to be 3 dots explode, become 1 dot, 1 place to the left. All right, let's just do it for fun. Put in 1 dot. Not very exciting. Zoom, stays as 1 dot. Put in a 2nd dot, always the rightmost box. Zoom. This time still not very exciting because they'll stay as 2 dots because you need 3 dots now to explode. Here comes the 3rd dot. With dot number 3, here it comes, rightmost box, zoom. 3 dots explode, kaboom, disappear, and replaced by 1 dot, 1 place to the left. So the code for 3 is now 1, 0. So these codes are a little bit different. Put in a 4th dot, always the rightmost box, zoom. 1, 1. Put in a 5th dot, zoom, always the rightmost box, 1, 2. Put in a 6th dot. Can you see in your mind's eye what the code is going to be before I actually bring in that 6th dot? Here it comes, zoom. 3 dots in a box, kaboom, they explode. 1 dot, 1 place to the left, 2, 0. And again, hours of fun. If I wanted to, I could try to work out 13. But again, I'm taking a deep breath because I think it's hard. You know, I'm just being honest, I think it's hard. But then, oh my gosh, more flashes of insight. Instead of doing a 2-1 machine or a 3-1 machine, I realized I could do a 4-1 machine or a 5-1. Or actually, let's be crazy. Let's be really, really crazy because this is the magic moment. Because when I had this epiphany, I went up to a 10-1 machine because I was feeling particularly audacious at that moment. And I decided I'm going to put in the number 273 into a 10-1 machine. I'm going to put in 273 dots in that rightmost box. And I see we have 19 minutes left, so I've got plenty of time to actually do it. Here goes, 273 dots in the rightmost box. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Yeah, I guess you can't yell at me right now to stop, but yell stop when you think I've got 273 dots yet. And I'm going to imagine I'm hearing your answers. No, 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 someone's saying stop. Someone's okay, 273 dots. Someone said stop. I heard it. I saw the hands. All right, 273 dots. Okay, obviously, I should have put all the dots in there right away because we know there are going to be some explosions. So here's my first question. There are some explosions. How many explosions will there be initially amongst these 273 dots? You think yourself, okay, 10 dots explode to become 1. So every group of 10 will explode to become 1 dot over here. How many groups of 10 are there in 273 of them? I guess there's 27 groups of 10. Kaboom, dot, kazing, dot, kazoop, dot, kabibble, dot, kablip, dot. So it'll be 27 explosions. So I guess it's going to make 27 dots here. And now I'm getting lazy. Can I just write the number 27 rather than draw 27 dots? Hope that's okay. I guess some dots are going to be left behind. If there's 27 explosions, there are 270 dots exploded away, leaving what? 3 behind? How am I going to do this? My picture's going to get very messy. Maybe blue shows up. 3 get left behind in blue. That's good enough, maybe. Messy board, no worries. Okay, next question. Will there be any more explosions? Well, yeah, there's 27 dots in here. 2 groups of 10. 10 explode, kaboom. 10 explode, kabow. 1 explosion, dot. Second explosion, dot, leaving 7 dots behind this time. 4, 5, 6, 7. So what's the secret code for 273 and a 10-1 machine? 2, 7, 3. And then suddenly you say to yourself, oh my goodness, these machines are doing something. The secret code for 273 and a 10-1 machine is 273. What are these crazy machines actually doing? All right, so that's our next challenge. What are these machines actually doing? So let me go back to the beginning, which is what, the 2-1 machine, I think it was? Did I keep that piece of paper? Yes, I did. Clever me. All right, so let's think about it. So this is where 2 dots explode to become 1, and we've got these weird codes. So a dot there is always worth 1, because we set the game up that 1 dot there is always worth 1. But then whenever there are 2 dots in that box, 2 1s, so it's a 1 and a 1. That I guess adds up to 2. 2 of those dots in the 1s position, 2 1s make 1 of those, which is 2 1s. That must be worth 2. And 2 of these, 2 2s, kaboom, the same as 1 of those. This must be worth 2 2s, and 2 2s is 4. And 2 of these, we know, would explode, kaboom, to make 1 of those. This must be worth 2 4s, which is 8. And 2 of these would make 1 of these, 16. And 2 of these make 1 of those, 32. And 2 of these makes 1 of those, and I've just ran out of room. That's good, because I don't want to keep going. Beautiful. And in fact, you can see it. Like, for example, 6, we said was 1, 1, 0. Literally, a 4, 1, 2, and no 1s is indeed 6. Whoa, whoa. And 13, I bet we can now see what the code for 13 has to be. I bet I need an 8. I bet I need a 4, that gets me up to 12. If I do another 2, that gets me too high, but I need a 1. I have a feeling the code for 13 is 1 8, 1 4, no 2s, and 1 1. 1 dot, 1 dot, no dots, 1 dot. Welcome to base 2. Welcome to what's called binary numbers. And this is just a quirky machine I just invented as a kid. In this untrue story, I didn't really. But here's the thing. We actually use these numbers today because this is just like computers. Computers are based on little electrical switches that are either on, or off. There's only 2 states. So they can only represent all the mathematics in 2 symbols like 1s and 0s. This is really handy. All the mathematics can be encoded in 1s and 0s. This is perfect for computer science. Whoa. The 3-1 machine. Then I have a feeling that one's going to be great as well, because that's just going to be the same idea. So let me get rid of this paper that's showing through. Dots here are always worth 1, 1 dot. But now 3 of these, 3 1s, which you can't see it. Oops, hiding. There it is. 3 1s, the same as 1 of these. This is worth 3 1s. 3 1s is 3. And 3 of these, 3 3s, makes 1 of those. Whoop. So this must be worth 3 3s, which is 9. And 3 of these makes 1 of those. Must be worth 3 9s is 27. And 3 of these makes 1 of those. The next box, if I drew it, would be, what, 81. And 3 of those makes 1 of those. And I'm glad I'm right out of paper. Excellent. So what's the code for 13 going to have to be in a 3-1 machine? I think I'm going to need a 9. I think we're going to need a 3. That gets me up to 12. And I think I'm going to need a 1. Voila. 1 9, 1 3, 1 1, 1 1 1 is the code for 13 in a 3-1 machine. Welcome to base 3. In fact, there is talk of building what's called optic computers. That's going to be based on polarized light, where light could come in at one plane, or light could come in at an orthogonal plane. You can see my messy hands. I've got markers all in my hands. Or there could be no light. So actually, these are computers based on light that comes in one direction, or 90-degree direction, or not have light. which means it has 3 states. So you'll want to do mathematics with something that uses 3 symbols, like this one. This uses 0s, 1s, and 2s. So if they ever build optic computers, they have a much more efficient way to code numbers. They've got 3 symbols now to use and build much more efficient computers. Amazing. And then finally, this one that sort of blew my mind when I first thought of it, is the secret code for 273 is 273? Well, yes, because dots here are worth 1. Now 10 of these, 10 ones makes one of those, so they must be worth 10. And 10 of these, 10 tens makes one of those, they must be worth 100. And 10 of those makes one of those, must be worth 10 hundreds, it's 1,000, and so on. And look, we said the secret code for 273 is 2 hundreds, 7 tens, and 3 ones. We literally speak 10-1 machine. 200, I'm going to write it out in English, and 73. There it is. We literally say 200s. Yep, 200s. 7T. That TY is short in English for the number 10. 7 tens and 3. There they are. We humans speak 10-1 machine. We speak base 10. I've just discovered for myself in this untrue story how we humans like to write numbers. Actually, this actually begs a good question. Why do we humans obsess on the number 10 for matters of arithmetic and counting? What made us think 10 is the right way to go? If you think about it for a while, well, us humans normally are born with 10 of these things. Can you see them all? There they are, messy hands with markers and all the rest. We have 10 digits on our hands, so we think our hands and fingers and thumbs are natural counting. So we actually think 10 is the way to go for counting. In fact, we so believe that we even call these individual things here digits. And what do we call these individual things? Digits. It's no coincidence, the same word in maths and in our physiology, because we were so obsessed with our fingers for counting. Though I'll tell you, some cultures went base 20. So why do you think some cultures decided to go base 20 rather than base 10? If you think about it for a moment, you say, what about us humans thinks 20 could be a good thing for counting? And you realize, oh, they must be thinking fingers and toes. Wow. So some cultures actually went base 20, probably because they have 20 digits on it. We have 20 digits on our bodies. In fact, I live in the US. There's a very famous speech by a very famous past president, Abraham Lincoln, called the Gettysburg Address. And he begins it with the sentence, 7 years ago. And that's as much as I've ever memorized the Gettysburg Address. But you have to look at this, 7 years ago. How many years ago is that actually? And then you realize score is an old word for 20. He's actually speaking base 20 there. He's saying 4 20s and 7 years ago, 87 years ago. So Abraham Lincoln was speaking base 20 back then. In fact, to this day, say 87 in French. Now, I don't know French. My French is terrible, but it is 87, I believe, which literally means 4 20s and 7. Word for word, they say 4 27. So even in French, there's a little bit of base 20 still around. Now, some cultures actually went base 12. And that's a curious one because some cultures actually say, we humans have a very natural way to count to 12 on one hand. And they say, do this. Look at your 4 long fingers. They're each divided into 3 sections naturally. And you've got this pointer, your thumb. I've never seen it, but in parts of Southeast Asia and parts of India, people count like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Have you ever seen that? It's very natural for some people on this planet to this day to still count that way. So people think, some historians think, oh, because people counted 12 naturally in one hand, and 12 is a very nice number for basic fractions like halves of things, thirds of things, quarters of things. 12 could be good for everyday life. In fact, we have vestiges of base 12 to this day. How many items are in a dozen? 12. How many inches are in a foot? 12. Because often you might want half a dozen of something. That's a good 6 of them. Or you might want a third of a dozen. That's a good 4 of them. Or a quarter of a dozen. That's 3 of them. 10 is actually a really awkward number. I mean, halves are okay, but thirds and quarters are icky for 10. So in everyday life, some people say we should be doing base 12. Anyhow, I'm getting distracted. I have 10 minutes left to give you some amazing mathematics of base 10. So I will do what our Western society does and work in base 10. So let's go through some primary school maths now. And probably the first thing you learn to do in mathematics after you've learned how to write numbers and learn how to use place value is do addition. So something like 242 plus 135. And you'd probably say, well, that one's easy. What's that? 3, 777. Am I right? Now, if you're watching just then, you may have said, hang on, this James guy, he just did something crazy. Did you notice I went 2 plus 1 is 3, 4 plus 3 is 7, 2 plus 5 is 7? I went left to right. Most people say, no, you have to go right to left when you do long addition. Okay, go right to left. Do you get a different answer? No, you get 377. This is now a true part of the story. I remember being very strange for me as a kid. I was being taught in maths class, as taught in every class, I had to read from left to right. English class, history class, social studies, whatever I was doing, always read left to right, except in maths class. I was told to go right to left, which I thought was strange. Now you're probably saying to me, well, that's probably too easy a problem. That's the reason, you can't see what the reason is until you do a more tricky problem. So let me do a more tricky one then. How about I do, say, 274 plus 147? Why not? Okay, well, 2 plus 1 is 3, 7 plus 4 is 11, 4 plus 7 is 11. The answer is 311. And I'm right. I will draw you a picture to prove I'm right, but I'll do it in a 10-1 machine. So I said 274, okay, 274, I think I did that correctly. Please add 100, 4 10s and 7 1s. Okay, add 1 more 100, sure. Add 4 more 10s, piece of cake. Add 7 more 1s, not a problem. 7 more 1s, there they are. So how many hundreds do I have? 3 of them. How many 10s do I have? 11 of them. How many 1s do I have? 11 of them. 311. It is absolutely solid. It's mathematically correct. I am a professional mathematician. I give that my stamp of approval. The only issue is society thinks it's a weird answer. There's nothing mathematically wrong with it. In fact, I'll even tell you, 11t. I'm even saying the right thing, 11t. In the Middle English, they did actually used to say 11t or 11 tens. Back in the 1200s and so forth, 11t was a fine word. Just today's society thinks it's a strange word. They also used to say 12t for 12 tens. In fact, if you read the Hobbit and the Lord of the Rings, you'll find the hobbits there actually do say 11t and 12t because I think Tolkien was having fun with it still in that language. But yep, this used to be a valid word, but today, no, you can't say 11t. That's strange. Okay, in which case, there's nothing mathematically wrong with the answer 311t11. But can we fix it up for society's sake? You say, well, yes. I mean, if this is a 10-1 machine, we could do some explosions to make society happen. All right, so let's do some explosions and make society happy. So I'm going to choose this middle one, just to be perverse. 10 dots explode, kaboom, leaving 1 behind. So 1 dot left behind, there it is, an extra dot there. So the answer is 401t11. I even saying it correctly, 401t11. Okay, society still thinks I'm crazy, but okay, I'll fix up for society's sake because 10 dots here could explode. Kaboom! 10 dots explode. What, leaving 1 behind, that one up there. So 1 left behind, extra dot there. That makes 2 dots there. So the answer is 402t1. To 402t1. Now, society is very demanding. It doesn't let me say 2t. It wants me to say 20. I don't know why it changes the word on me, but it wants me to change the word there. Okay, you should say 2t, actually. Okay, 421. And of course, that's what you could do when you do the standard school algorithm. Because if you go, where is it? There it is. You go start right to left, 4 plus 7 is 11. And we say, well, actually it is 11. But you don't do that. You say, no, you can't write 11. You have to leave 1 behind and carry a 1, I think is the language you use. But what I just did, I took 10 dots here and I went kaboom and made an extra dot with the 10s. I did 10 dots here, kaboom, made an extra dot here. We're doing the same thing. Now I say 12, well, I can't say 12. I want to write 12 because it really is 12. I say, no, explode. 2 get left behind, extra dot there, 4. So the standard algorithm we learn in school, of course, is good and correct. It just likes you to go right to left and do the explosions as you go along, and they call them carries. I personally prefer to go left to right and do the explosions at the end. Here's the thing about mathematics. Everything that's good and correct in mathematics is actually good and correct. It's amazing. You can do it any way you like. If you're correct, you're correct. It's fabulous. I find it actually much easier to think this way because I see what's really going on, and plus it's kind of quirky and fun. Why not be quirky and fun in life? All right, so there's addition. So let me just do a couple more school algorithm type things at this beginning introduction to exploding dots. What if I did something like multiplication? 2784 times 3. Now, this seems scary, but you think, okay. If I liberate my mind and say, I don't care what society thinks, I'm just going to give myself a very natural, obvious, mathematically correct answer. I might say the actual thing I'm doing here is the following. I'm in a 10-1 machine, 2, 7, 8, 4, 2,000s, 700s, 8 10s, 4 1s. Yep. and I'm being asked to please triple everything. You say, oh, if I'm being asked to triple everything, what's the most obvious thing to do? Well, it would be to triple everything. Instead of having 2,000s, I'll now have 6,000s. Instead of having 700s, I'll now have 2100s. Instead of 8 tens, I'll now have 24 tens. Instead of 4 ones, I'll now have 12 ones. Beautiful. The answer is 6, 21, 24, 12. I'll just put some vertical lines in there to make it easier to read. Beautiful, I am done. And that's mathematically correct. And here's the fun thing. How would you say that number? Try saying it in your mind's eye right now, or your mind's mouth, or your mind's, I don't know what the expression is. It's totally quirky and fun. Okay, 6,000, 2,100, 2040, 12. Maybe something like that. By the way, that spells out how strange society is. Saying 2040 seems weird. Does saying 2100 sound weird to our ears? The funny thing is, society lets me say that one and says, no, 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 you wouldn't dare say that. Don't be silly. All I can say is society is fickle. It's really fickle. I don't get the demands of society. They're just all over the place. So what we do, fix it up for society's sake. So I could say something like this, leaving 4 behind. 4 get left behind, and kaboom, kapow. That makes for 23 dots there now. Okay, so fix it up for society's sake. So the answer is 6,000, 2,300, 40, 12. Maybe 10 explode here, leaving 2 behind, an extra dot there, so 5. I'm being fast now, I hope it's not too fast. 6,000, 2,352. Actually, it should be 52, shouldn't it? 52, but we say 52. Society, what can I say? I guess that people don't like the 23 there, so 2 explosions, leaving 3 behind, extra 2 dots there, make 8, 8,352. Beautiful, beautiful. Multiplication, I love it. Ah, exploding dots. Actually, multiplication is really closely related to something else called division. Let me do a much easier multiplication problem first. 1203, say times, well, let's just do times 3. We can see in our mind's eye right away, it could be 1,000 becomes, 3,000s, 200s becomes 600s, no 10s stay as no 10s, and 3 ones become 9 ones. The answer is 3609. In fact, here's the picture of what we just did. I said, start with 1 dot, 2 dots, 0 dots, and 3 dots. And now just please triple everything. So I'm going to literally triple everything like this. 1 dot becomes 3. 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 It's a very tedious way, but I tripled that dot. I tripled that dot, tripled that dot, tripled that dot, tripled that dot, tripled that dot. Bingo. And there's the answer. 3 dots, 6 dots, 0 dots, 9 dots. 3, 6, 0, 9. Because look what would happen if I asked instead to go backwards, which people call division. Start with the answer and divide by 3. You say to yourself, oh, okay, let me draw 3, 6, 0, 9. 3, 6, 0, 9. And I'm asking, how many groups of 3 can I see in that picture? And I say, oh, groups of 3 dots. Okay, division means how many 3s can you see in a picture of 3, 6, 0, 9? Well, I see 1 3 right there at the thousands level. I see another group of 3 there at the hundreds level. In fact, I see a second one at the hundreds level. I see none there. But I see 3 groups of 3 at the ones level. Oh, I see 1 at the thousands level, 2 at the hundreds level, none there at the tens level, but 3 at the ones level. I see, oh, 1, 2, 0, 3 of them, which is exactly 1 group there, 2 groups there, 3 groups there. Exactly what we did for multiplication, which means I can now do division by drawing pictures, just by thinking my picture for multiplication, but backwards. So in the remaining -1 minute, which I see we have, let's try something like, I don't know, 4, 8, 1, 2 divided by 4. Let's see if we can do a straightforward one first, and then we'll end off with a trickier one.
I'm going to interrupt you there now. I've got to call you the doctor in future since you've got -1 minute left.
Oh, okay. All right. The doctor, yes. I know what the reference is. 4, 8, 1, 2 divided by 4. What does 4 look like? Well, that's 4 dots. Do I see any groups of 4 dots in that picture? Why, yes, there's a group of 4 dots, 1 at the thousand level. There's a group of 4 dots at the tens level, hundreds level, another one at the hundreds level. Brilliant. Ooh, and I don't see any more dots. And I'm panicking. Do I see any more 4 dots? What could I do to see some more groups of 4 dots? And you say, okay, I guess I'm stuck. I'm just going to give up. I'll go for a walk. I'll do something else. I'll fry an egg. I'll do something. Oh, in fact, there's something I could do might even be relevant to the problem. Doesn't it feel tempting to unexplode that dot? Is that a crazy idea? Could I say that dot there was really coming from 10 dots over here? Is that a wild idea? I guess I could need a sound effect for explosions. It would be if explosions were kaboom, maybe unexplode is like a moo back or sucking sound. Who knows what? But look at that, what it did for us. Because I've got another group of 4 dots there, another group of 4 dots there, and another group of 4 dots there. The answer is 1, 2, 0, 3. Oh my goodness. I wonder if that's the same thing that I was taught to do at school. I'm having to do that in school. In fact, let me finish off the very strange story. I'd been trained in my maths classes. Everything in maths classes is right to left. Every other subject in school was left to right, except maths class for 5 years of my life was right to left. But now I was told, no, we're going to do this thing called long division now. Now you just start left to right. You can say, how many times does 4 go into 4? Well, once. 4, subtraction, you get 0. Bring down the 8. This is very weird. How many times does 4 go into 8? Twice. Oh, great. With 8, 0. Bring down the, 1, don't know. So bring that one down as well. 12, 3 of them. So here's my mystery for today. When I was a 10-year-old, 11-year-old in grade 5 back in Australia, I could do the long division, but I was absolutely aware that I did not understand what was going on. This I actually understand. Now, of course, my teachers were fabulous and good. They were teaching me good, correct maths, but they didn't explain why it was working. So here's my optional homework for today after today's speed introduction to exploding dots. Optional means don't do it under any circumstances, by the way. Can you look at this picture, compare it to what you were taught in school, and see actually you are doing the same thing? Can you see these two methods mesh up? The only thing here is I bet this is my picture of dots and boxes without a picture of the dots and boxes. If we could only draw pictures to go with this, life would be good. So, optional homework for tonight. Can you see how what we were taught in school meshes what I've discovered of myself in this untrue story? And then we can start doing more complicated long division, like multi-digit long division. See if you can work out something like this one. That would be cool. Can you do it with dots and boxes and compare it how you were taught in school? All right, on that mysterious note, I think I shall stop for our first introduction of exploding dots at that point right there. So thank you everyone for listening. If you made it to the end here, I am so proud of you. I think you're awesome. I may know you or may not know you, but you're awesome nonetheless. So thanks so much for joining.
We've had about at least 20 viewers at least. So you were held quite, we've already had one person just join, which is a bit sad. But,
what? But it's been video recorded, has it not?
Yes, it's all right. It's okay. It's all with law. You'll have to watch the rerun, Doody.
Okay. So now can I show off my quail mug from Phoenix? I live in Phoenix, Arizona, and these birds are in our backyard all the time. So I'm just showing my quail mug.
And they've got baby rabbits and teeny weeny itsy bits. How big are the rabbits? Because you can.
Oh, we've got I mean, you can't see on a Zoom camera. Okay, from my nose to my, so tiny rabbits about that big, and the bigger rabbits this one. And then we have jack rabbits out in the actual desert that are big rabbits.
So James gets to climb the Phoenix Mountains every day, which makes me, I don't feel jealous, but I'm very happy to see pictures.
I'm very sensitive to the fact that people are stuck in very limited quarters right now, and I don't want to be boasting about the fact that I've got the wilds out there in my backyard, which I go traipsing in most every day. What can I say?
We're on again on Thursday. We've got fractions. Everybody's favorite request, help me with fractions. James,
let's have a little bit of fun with fractions. Let's just have fun with it, and then the help will come along the way. Just play, and then they'll naturally help with the fractions.
And my favorite thing, folding a tie in thirds. When I saw James's video of folding a tie in thirds, everyone get your ties ready. Thursday night, 8 o'clock. And thank you so much for joining us. There'll be loads of links up, down, somewhere around. And it'll also be available on YouTube. So thank you so much. And I'll see you on Thursday.
See you all. Thanks for coming. Bye.
Thanks. Bye.